This first integral is just going to give us this piece of a sphere, and we have 2 pi, and then the integral of sine phi is negative cosine phi, and that's going to be evaluated from phi naught, still need to figure that out, up to pi over 2, and then we'll have 1/3 a cubed coming from integrating the radius. That's good. That makes it pretty clear that we're getting a volume out of this. And so cosine of pi over 2, that's just 0. And so this is, okay, plus the other integral, which I'm going to call integral 2. So this is 2 pi over 3 a cubed cosine phi naught. And so now it's really time to think about that question, what is phi naught? Here's what we know about phi naught. If this is the RZ plane, we know that we go up to a height h and we go out out a radius a, and that this is the angle phi naught. And so actually, we know cosine of phi naught. It's h over a. And so this is 2 pi over 3 a squared h plus I2 plus I2. And so now we just need to figure out what this second integral contributes, because we figured out the contribution from this wedge out of the sphere. Now it's time for the integral of our cone piece. The d theta part just contributed to 2 pi. And so we integrate with respect to rho first, and let's just focus on I2. So that's this integral. So I2 is the integral from 0 to phi naught of sine phi times 1/3 rho cubed. And so when we plug in the endpoints, that becomes h cubed over cosine cubed phi. And this is going to get integrated d phi. And so, oh, skip the 2 pi out front, can't forget that. So this is 2/3 pi h cubed, the integral from 0 to phi naught of cosine to the -3 phi sine phi d phi. This is something really nice, actually. It looks a little bit annoying, cosine to the -3, but luckily we have that sign right there, and so this is very natural for a u substitution. So if we set u to cosine phi, then du is negative sine phi d phi. And we just need to think about the bounds. When phi is 0, u is equal to 1. And when phi is phi naught, well, we have already determined that the cosine of phi naught is h over a. So u is h over a. Completing our u substitution, we have 2/3 pi h cubed, and so our cosine to the -3 became a u to the -3, our sine d phi became a negative du, and our bounds went, instead of cosine being 0, u is 1, instead of phi being 0, u is 1, instead of phi naught, which we never determined, the cosine of phi naught is h over a. So that's quite convenient, and now we're certainly ready to integrate. Okay. So 2/3 pi h factors out times a squared plus h squared times our integral, and our integral is negative u to the -2 times -1/2 from 1 to h over a. Okay, and so we have 2/3 pi h a squared plus h squared over 2. And then the upper bound becomes a squared over h squared minus the lower bound, which is 1. And now simplifying, this is 2/3 pi h a squared plus a squared over 2 minus h squared over 2. And so this is a 3/2 a squared, and so we get pi h a squared minus pi h cubed over 3 as the final volume of the water in the tank. If we wanted to check this, we could complete the integrals back in cylindrical coordinates. The one coordinate system we haven't dealt with yet is Cartesian. And so as the last thing I do, I'd like us to think about how to write this coordinate system in Cartesian, this volume in Cartesian coordinates. One way to proceed is to use that same cross section that we had before. Now it's in the ZY plane. And if we think about this cross section in Cartesian, maybe we integrate in Z first, in which case for sure we can represent this region without a problem. But in Z, this outer region that's getting spun around in Cartesian, that's going to be a bit of an issue. The Z bounds aren't bad, but the region in the XY plane over which that region lives is this one. And that was very straightforward to express in cylindrical, but it's going to be really hard to describe this disk, this piece of a disk in Cartesian. And so actually to do this integral in Cartesian, I think our easiest option is going to be to consider the whole space and subtract off the little bit that doesn't have water in it. And so that integral over the whole space, well, this is an integral over a half ball. And so I get to fill this in to do that integral. Negative a. So let's say x is going from negative a to a. And then y is going from this lower curve to this upper curve. And so we recognize that as the negative square root of a squared minus x squared up to the square root of a squared minus x squared. And z is just doing the hemisphere. So it's going from z up to the square root of a squared minus x squared minus y squared, dz, dy, dx. And so that is the volume that we would get if we had a solid half hemisphere. And of course we know that volume. It's 4/3 pi a cubed divided by 2. And so this integral should give us 2/3 pi a cubed. And the question is, what are we subtracting off? How do we set up the bounds of the region that needs to get subtracted off because it doesn't have water in it? By construction, this region is also above a disk, but now that disk is of radius square root of a squared minus h squared, and the height is going from h up to the sphere. And so this is an integral. Y is going from one side of the circle, negative a squared minus h squared. I'm actually going to call this quantity, this a squared minus h squared, I'm going to call it b squared, up to b, where b is the square root of a squared minus h squared. And then the integral to deal with the y from the lower piece to the upper piece of this disk. And so that's the square root of b squared minus x squared, the negative square root, because we want to be down here, up to the square root of b squared minus x squared. And then we're going from h up to the sphere, and the sphere is a squared minus x squared minus y squared, just as before, and then this is dz, dy, dx. So this integral gets subtracted from, so negative of this integral gets added to 2/3 pi a cubed to give us the volume of the water in the tank.